This video is all about hexadecimal, which is base 16. Now you might wonder why you would want to learn about the number system base 16. And the reason why is because in computer science, hexadecimal is used as a shortcut or shorthand for binary. And you'll see why in a few minutes. Okay, so first of all, if it's base 16, there needs to be 16 symbols. So the 16 symbols are 0 through 9, and then for the remaining 6, we use A, which is equivalent to decimal 10, B, which is equivalent to 11, C, 12, D, 13, E, 14, and E, 15. Now, when we convert a hexadecimal number to decimal, we just simply use the place values. So if you look at the number 25, which is base 16, this is the ones place, the 5 here is the ones place, and the 2 is the 16's place. So then the way that we convert it is simply by taking 2 times 16, which is 32, plus 5, which is in ones place. 5 times 1 is 5. So 32 plus 5 is 37. Okay, let's try a couple more. 4F. So 4 is in the 16's place, so it's going to be 4 times 16 plus F. Remember, F now is equivalent to decimal 15. So that's going to be 15 times 1. So 4 times 16 is 64, plus 15 is 79, base 10. Okay, the next one is A7, hexadecimal. A, recall, is 10. So it's going to be 10 times 16, which is 160, plus 7 times 1, which of course is 7, or 167. And the last one, BC. B is equivalent to decimal 11, so that's going to be 11 times 16, plus C, which is equivalent to decimal 12, 12 times 1. So that comes out to be 188. Okay, now converting a decimal number to hexadecimal. Okay, this procedure is very much like converting a decimal number to binary. And if you remember, the way that we did that was we divided repeatedly by 2, and we used the remainder and the quotient. Okay, so we're going to do a similar procedure here, except we're going to repeatedly divide by 16. So we'll start out with this number right here, 35, base 10. And what we'll do is take that 35 and we'll divide it by 16. And that's going to give us a quotient of 2. 16 times 32 is 16 times 2 is 32, and a remainder of 3. So the least significant hexadecimal digit is 3. Now we take that quotient of 2 and we divide it by 16, which of course gives a quotient of 0 and a remainder of 2. And so our final hexadecimal number then is 23. So 35 decimal equals 23 in hexadecimal. Okay, let's try another one. 42 base 10. We're going to divide that by 16. That gives us a quotient of 2 and a remainder of 10. Now remember that we have to convert this to a hexadecimal symbol. So the least significant hex digit is going to be A. And then we take that quotient of 2, we divide it by 16, which gives us a quotient of 0 and a remainder of 2. So the hexadecimal number is 2A. Okay, here's another one, 173 base 10. We're going to divide that by 16. That gives us a quotient of 10 and a remainder of 13. So that least significant digit now, we have to take that 13 and use a hex symbol. So that's going to be D. Okay, now we take the quotient, we divide that by 16, and of course that gives us a quotient of 0 and a remainder of 10, expressed in hexadecimal is A, so the final hexadecimal number is AD. Okay, now sometimes you're going to want to do this on a calculator. Some of them are simple. You don't need a calculator, but some of them, calculator comes in handy. So let's try 180 base 10. You want to convert that to hex. So when you divide 180 by 16 on a calculator, you're going to get 11.25. You don't get a quotient and a remainder. You get this is the quotient, the 11, and this is in fractional form or decimal form. So if you just take that 0.25 and you multiply that by 16, that'll give you the actual remainder. So the remainder is 4, okay? And as you probably noticed on the previous slide here, as long as that quotient is less than 16, all you have to do is convert it directly to hex. So in this case, the quotient was 11. So in hex, that's B. So the answer is B4. All right, let's try another one. 157 base 10. We want to convert that to hex. We get our calculator out. We divide it by 16. It comes out to 9.8125. So we take that fractional part here, or decimal part, 0.8125. We multiply it by 16, and that gives us 13. Okay, now 13 is equivalent to D in the hexadecimal system. And then we just take the 9, and that is our most significant hex digit. So the final answer is 9D. Okay, so now we get to the point where you will be able to see why hexadecimal is a good shorthand for binary. So to convert a hexadecimal number into a binary number, it's very simple. First of all, we're going to be working mostly with 2-digit hex numbers, but what we say here can be extended to 3 or 4 or whatever. All you have to do is take each hex digit individually and convert it directly to a 4-bit binary number, and that's it. Now, just one thing here. Remember that the biggest hex digit that you can get, that you can have, is F, which is equivalent to the decimal 15. And in binary, that's 1111. So that's the biggest 4-bit binary number that you can have. So it'll all work out. Okay, so here's an example. We have this number, 59, which is in base 16. So we take that 5 and convert it directly to binary, which is 0, 1, 0, 1. This is 1's place, 2's place, 4's place, so this is 5. And then we take the 9 here, and 4 bits, 1, 0, 0, 1. This is the 1's place, 2's place, 4's place, 8's place. 8 plus 1 is 9. So 59 in hexadecimal is equal to 010110001 in binary. Okay, that's all there is to it. Here's the next one, 8C. Okay, 4 bits for each number. We take the 8, and that is 1000 in binary. And then C, remember C is 12, so that's 1100. That's 1, 2, this 4's place, the 8's place, 8 and 4 is 12. Okay, so 8C is equivalent to 10001100. Last example here, FA, hexadecimal number. You want to convert that to binary. As I mentioned before, F in binary is 1111. This is 15. And A is 10. In binary is 1010. So therefore, it's 11111010. Okay, so the last thing we have to do is to convert binary to hexadecimal, going the other way. And this is just like you would expect. It's just the reverse of what we had on the last slide. So what we do is we start with the least significant bits and arrange the bits in groups of 4, and then convert each 4 bits directly into hexadecimal. Okay, so here is the first example right here. This binary number is 0110010001. So I start over here and I count for the first 4 to the left here, so that's 1001, and then the remaining 4 is 0110. And then just take each one of these groups of 4 and convert them to hexadecimal. So this is going to be 6, and this is going to be 9. So 69 in hexadecimal. Okay, the next one, 110001111. Okay, I'm going to arrange them in 2 groups of 4, starting from the least significant bit to working to the left. So that's 11100011. Put a space in here just so you can see the arrangement of 4. And now convert each one of these directly to hexadecimal. So 1100, that's 12. In hexadecimal, that's C. 0111, that's 7. So C7 in base 16. Okay, here's the next one. This is 11111010. Okay, as we've seen before, 1111 is equivalent to decimal 15 or hexadecimal F. 1010, that's equivalent to decimal 10 or hexadecimal A. So this is FA, base 16. Okay, here's an example where we have a 10-bit number. Well, it doesn't really matter. It's just going to be 3 hex digits instead of 2. But we work the same way. We start over here all the way to the right, to the least significant digit, and we count off 4 and put them in groups of 4. So we have these least 4 over here, the next 4, 1011, and then the last 2 is 11, but we can just put 2 zeros in front of those to make it a 4-bit number. And then take each one of these directly and convert them into hexadecimal. So the 11 is 3, the 1011, that comes out to be 11, which of course is B in hexadecimal, and then the 0111 is 7. Okay, the last one is all ones, and we group them in 2 groups of 4, all ones. 1111 is 15, 15 in hexadecimal is F, so it's FF in base 16.